Good evening, everyone. I am Himanshu Shekhar Das, Assistant Professor, Department of Production Engineering, IGIT Sarang. So, welcome to the course Machining Technology. And already we have discussed about this course in our regular class. So, till now, before starting up the class or starting up this lecture, I just want to recall those things. So, whatever we have discussed in your regular class. So, we have already discussed the machining technology, introduction to machining technology. In that, what is machining process, what is metal cutting process, what are the types of tools that are used in machining process. One is single point cutting tool, multi-point cutting tool, and their differences. Next, we have discussed the tool geometry of the single point cutting tool, multi-point cutting tool, and the different systems of your tool signature, that is ASA, ORS, NRS, American Standard Association, ASA, ORS, Orthogonal Lec system, and normal Lec system, and how they differ to each other, and the 7 parameters which defines the tool signature or tool nomenclature. Those things we have already discussed. Next, the conversion of ASA to ORS or ORS to ASA, and then the effect of cutting tool geometry on machining process, how it is affecting. And also we have seen how a chip is formed during machining operation, the mechanism behind the chip formation, and the types of chips like your continuous chip, discontinuous chip, and the formation of built-up edge in a continuous chip. All the things we have covered till now. We have already seen the difference between orthogonal cutting and oblique cutting. What is orthogonal cutting, what is oblique cutting, and their differences, and the chip breaker, the need of chip breaker during machining process. So next we will start the machining in this lecture, the analysis of orthogonal machining. So what is analysis? What do you mean by analysis of orthogonal machining? Here analysis means generally all the plants, they are focused about how much they are giving input and what are the outputs they are getting. So in between input to output there is something that will convert that input to output. So here we are talking about a machine. How a machine converts the input in form of raw material to a particular product, a mechanical elements or something. So in that what we are analyzing? We are analyzing how much force is induced during the machining operation. If we know the force, we can calculate the power consumption. If you know the power consumption, then we can know the prime mover required for that machine, or our input, how much input we are giving in terms of cost or in terms of money. So another example is like a tool life. How many tools you need, what type of tools you require for a particular machining operation, how many days the tool will survive, and the temperature, how it will sustain the temperature or the induced temperature during machining operation. Next, the types of tool materials. Next, what type of coolants you have to use. All are different types of analysis of a orthogonal machining operation. So we'll see one by one the various type of analysis, and we'll go. So before analysis of anything, you have to assume something. So here the assumption in orthogonal machining are: first, the tool is perfectly served, we assume, and there is no contact along the clearance phase. Means during the clearance phase or during the machining operation, there is always some clearance between the tool and the workpiece. Next, the cutting edge of the tool remains normal to the direction of the tool feed or work feed. Next, the direction of the chip flow velocity is normal to the cutting edge of the tool. We assume there is no sideward movement of the tool chip, and the chip doesn't flow to any of the sides. Next, we assume the cutting edge is a straight line extending perpendicular to the direction of motion and generates a plane surface as the work moves past it. So whenever the tool is moving along a workpiece, we assume that the machine surface is a plane surface. Next, the depth of cut is constant throughout the operation. width of the tool is greater than that of the workpiece, and the work moves relative to the tool with uniform velocity. There is always a uniform velocity throughout the operation. Next, a continuous chip is produced with no built-up edge. So you will always assume that the chip is produced chip is a continuous chip and without any built-up edge. So these are the assumptions we have taken or we have made before analysis of any orthogonal machining process. So first we will see the chip thickness ratio. From the name itself we are knowing that there is a ratio between something. So here it is an index of the amount of plastic deformation which the metal into chip has undergone. Means normally the plastic deformation, how much plastic deformation, and the means of plastic deformation, how it is changing the metal into chip, that we can calculate or you can know about this ratio from this chip thickness ratio. It is noted by R, not denoted, and I have taken R. Some books they have taken zeta, some books, so different names, different notation is. So don't confuse the tool signature that R, that is nose radius, and here R is the chip thickness ratio. So what is chip thickness ratio? It's the ratio of the uncut chip thickness to the cut chip thickness. So ratio between uncut chip thickness to the cut chip thickness is called chip thickness ratio. What is uncut chip, cut chip, we'll see next. So let assume T1 is the uncut chip thickness and T2 with the cut chip thickness. So chip thickness ratio is T1 by T2 is equal to R. So this is the model of a machining process. This is the workpiece, this is the tool. The tool is moving along this direction. So as the tool is moving along, this is the VC, cutting velocity vector, which is along this direction. This is the thickness which to be removed by the tool for in one single pass. So this thickness is called, or which is not machined till now, that is called uncut chip thickness, which is T1. Next, the chip which is formed during machining operation, there which has also a thickness. So that thickness of the chip is called T2, which is cut chip thickness. And already we have discussed in the mechanism of chip formation how the chip is forming because of a shear plane, and the plane which is shear plane is here. This one is the shear plane. If you see here, the shear plane is making some angles with their cutting velocity vectors. That angle is beta. So beta is here is called shear angle, which is the angle between the shear plane and cutting velocity vector. And gamma, here you have written gamma. So gamma equal to gamma B, all are back rag angle. Here it is a positive back rag angle. So gamma or gamma B. This one is the Vs, the shear plane velocity or shear velocity, which is the velocity of the chip with respect to workpiece. Velocity of the tool with respect to workpiece, VC. Velocity of the chip with respect to tool, that is VF. We will see in future what is VF and how they are related, VF, VS and VC. So you have known what is T1 and T2. T1 is the uncut chip thickness, T2 is the cut chip thickness, and ratio between those are chip thickness ratio. So VC, cutting velocity, already discussed. Cutting velocity or velocity of the tool, VS, chip velocity or velocity of chip relative to tool. VS, shear velocity or shear plane velocity or velocity of chip relative to workpiece. Gamma is equal to gamma B, back rag angle, gamma. Beta, shear angle, angle made by shear plane with respect to cutting velocity vector. Beta, shear plane with respect to cutting velocity vector. B1, B2, width of the chip before and after the machining operation. So B1 is before machining, the width of the chip. B2 before machining, after machining, the width of the chip. L1 and L2 are the length of the chip. Length of the chip, before and after the machining of L1 and L2. So if you see the machine part here in a 3D view, then this is the work part. Here this is the machine surface, this is the shear plane, this is the thickness to be machined, that is uncut chip thickness T1. Here the chip which is already removed, that is T2, and B is the width of the chip, which is B1 and B2. B1 is before machining, B2 is after machining. So we assume that width of the chip is assumed to be constant and there is no sideward flow of metal. So what this signifies, B1 equal to B2 is equal to B. So the width is always constant. And why we are assuming like this? Because during machining operation, the forces applied by using the tool is acting like a compressive force in the length direction. What are the force exerted by this tool during the machining operation? Which is along the length direction, and there is a compressive force. So if it is a compressive force, some amount of volume may be compressed or decreased where in the length direction. And as we know, the volume is incompressible, so the volume must be increased in the other two directions. If the volume is decreased in the length direction, then that volume has to be increased in either thickness or width direction. As the thickness direction is weak, the volume of chip is increasing only on thickness direction. Thickness means as the thickness direction is weak compared to the width, the volume of decrease by the tool will be increased along thickness direction. So therefore, the thickness T2 or the cut chip thickness is always more than uncut chip thickness, and the width of the chip remains constant because there will be no change of volume in the width direction. So we have taken B1 equal to B2 is equal to B, and T1 and T2 are not equal. T1 is smaller than your T2 because of this compressive force. And again, from this volume is incompressible, we can write T1 B1 L1 is equal to T2 B2 L2. The volume is always constant. So T1 by T2, T1 B1 L1 means the volume before machining, and T2 B2 L2 volume after machining. So T1 by T2, if we arrange, is equal to L2 by L1 equal to R. Likewise, T1 B1, if you consider the volume rate, volume per second or per time, T1 B1 Vc is equal to T2 B2 into Vf. Vf is the velocity of chip flow, cutting velocity. So T1 by T2 is equal to Vf by Vc equal to R. If you combine these two, we will get T1 by T2 is equal to L2 by L1 equal to Vf by Vc, which is we have noted R, which is always less than 1. Why it is less than 1? Because if we consider the, already we have discussed the chip thickness, which is always more than the uncut chip thickness. And as the compressive force exerted by the tool along the length direction, so length of the chip after machining must be less than before machining. If we compare the two lengths, the length produced with the length of the chip produced, that length to the uncut chip length, then you will get the less, you will get the smaller chip length compared to the uncut chip length. In the same way, if we compare the thickness of the chip thickness is always greater than your uncut chip thickness, or the T2 is always greater than T1. Therefore, the ratio is always less than 1. So during calculation or during problem, if the ratio is greater than 1, then your chip thickness ratio is wrong. Just reverse it. So in that way, we will calculate the chip thickness ratio, and it will index, which will show the plastic deformation during the machining operation. And okay, next class we will discuss about the velocity relationship. Thank you.